This one is already working. This one is first of all, it's really nice. Did you check that it works?
Yeah, it works.
Ah, yeah. So you can see this is how
yeah. Yes, good. Thank you.
Okay. Okay. Oh, microphone's on. Okay. Okay, so it's my pleasure to, for the third time this week, introduce Philip Kim. Right, so there was a public talk. Sorry, Philip. There was a public talk on Monday for like a generalized audience, and yesterday we heard about thermal transport. And so today we're going to talk about quantum Hall effect and anyon, search for the anyon statistics in quantum Hall interferometers. And again, just a quick introduction. So Philip Kim is a full professor at Harvard University. He's an expert and one of the pioneers of two-dimensional materials. He was the first to observe the quantum Hall effect in graphene. He was the first to work on van der Waals heterostructures and so on. So many thirds in the field of two-dimensional material. And for his work in particular, again, on the quantum Hall effect in these van der Waals heterostructures, Philip received a lot of prizes. Just to select two of them, the Buckley Prize from the APS, so the most prestigious condensed metaphysics prize in the US, and last year the Benjamin Franklin Medal of the National Academy of Sciences. So with this, we'll go over to the presentation. Okay, thanks, Philip.
Good. Thank you, Dimitri. Yeah. All right. Let's see. Oh, it's up. Good. Great. Thanks. All right. Thank you. Thank you very much for the introduction. Third times, 3 days in a row. I think that's one thing you missed it out is actually I'm a thesis advisor of the Professor Dmitry Afetov. That was my honor proud. Yeah, so I think that's something good. So in this my last talk out of this 3 series, I want to kind of tell you about the story to this anyons and creating anyons in the quantum materials, and we'll give you a little bit of broad overview as well as some the development. In fact, the development I'm going to tell you is not even published yet, not even written of some part, but nevertheless, I think shows them the where we are and where we are going type of the stories. It's more like the quite open-ended. Because we are going to talk about the anyon, probably it's a good starting point that what we mean by the anyon. We know that when we have the two identical particle or any kind of identical particle in quantum mechanics, because of this symmetry of this indistinguishableness of the particle, we know that when we changes the particle indices, we should come back to the kind of same description in quantum mechanically. And that symmetry dictates that any particle that live in the three-dimensional up can be categorized either boson or fermion, depends on to the after this symmetry operation, exchange operation, where the wave function changes sign or not, no change of sign, right? So that's kind of the two possibility only we have for the three-dimensional up. However, it's been known for a while that this story is a little bit different once you get into 2-dimension. Once you confine the particles into the 2-dimension, this exchange operation, or that more like if you start kind of exchanges or double exchanges and make a kind of one complete turn, because of this winding number in the 2-dimension is well-defined, or the well-defined topological invariant. Because of this winding number, there's other possibilities arises when you just write down quantum mechanical wave function for particle exchanges. So it's been figured out the kind of few people and just kind of write down that finally we'll check. And idea is once you just kind of 2 dimensions and then, oops, okay, sorry. Okay. Once you just kind of write down the part, then you will see that either if the ground state is not not degenerated, it can carry the phase, and the phase doesn't have to be 0 and pi, and it can be some kind of fraction of this pi is allowed. And especially when ground state is a degenerate cases, some cases after exchanges to the particle indices, the ground wave function can in principle map into one to the other one, such that it can be connected by some sort of unitary operation, which in principle doesn't have to be commute each other. And therefore, there's even just kind of distinctions. This is abelian cases, and this is non-abelian cases can be categorized in that way. This idea came in from the Wilczek, and often that this is named as a kind of anyons, and depends on to the ground state properties. Anyon can be so-called the abelian anyon, which means that it comes with the sum of the this fraction of charges after exchanges, or it can be just kind of unitary operators that describe the exchanges can be appears, often called as a non-abelian anyons, right? This anyon has been kind of discussed theoretically quite a bit, but also it becomes kind of quite important in kind of in this era of the quantum engineering or science and engineering. Part of the reason that if somehow you just furnish the especially non-abelian anyon, because of this, the exchange operation, often called the braiding operation, is a way that you can encode the informations, entangle the states, quantum mechanical state, spatially distributed by just kind of this braiding operation, which can be immediately useful for the fault-tolerant the quantum information processing. And hence that there has been some of the interesting idea that getting this non-abelian anyons and try to use this as a kind of fault-tolerant quantum computing. This idea, in fact, is not only just physically carried out in non-abelian anyon, but also many of these the quantum algorithm coding-wise. That one way is just try to create kind of mimic this non-abelian anyons and try to kind of fault-tolerant the computings in that kind of the quantum algorithm way. So this idea has been kind of widely spread it out. And of course, as an experimental physicist, one of the exciting ideas is there a way that we can realize those kind of non-abelian anyons or anyon in general in the real space. And of course, although anyon can be the fundamental particle per se, we know that most of this fundamental particle we know is actually a 3-dimensional up. Therefore, the creating anyon requires some of the emergence system in the low dimension, especially in 2-dimension. An interesting system one can look for is, of course, of the fractional quantum Hall states. Indeed, in the fractional quantum Hall, it was kind of first realized, and certain fractional quantum Hall state, especially 5 half the fractional quantum Hall states, which is considered as just the condensation state of the composite fermion, was believed to be create non-abelian anyons in the system. And later on that some of the combination of the superconductor and other topological system, is various topological system, also proposed to create this non-abelian anyon, often called this the Majorana quasiparticles. This has been kind of theoretically proposed, and some of the experimental steps has been made. Yet the really smoking gun evidence of any of this discovery of non-abelian anyon experimentally is still being challenged when that kind of both of the platform. So it is a kind of open problem, especially in the experimentally, and a lot of experimental approach happens for various type of platform, as I just listed a few papers here. So what I'm going to tell you today is my group's approaches on some of this platform that I'm going to, time allows that I will start with probably the first part that here that the quantum Hall based the anyon creation. And if time allows, I will just kind of briefly discuss about second platform that realize, especially based on kind of 2-dimensional system. Okay, so with that, let me start. By the way, you're welcome to ask any questions anytime. So let's make it a little bit more interactive way. Especially, I'm still under the jet lag. So before I just fall asleep, I wish to have a little bit of the excitement among audience. Okay, so the first part, I'm going to talk about the anyon in the fractional quantum state, especially realizing graphene. This required. This has several collaborators. Here's the Tom Verkmeister is the main students who carried a lot of work. We have the collaboration with Ami Jacobi's group. Theory collaboration is both Halperin and Dima Feldman, and that of course the HBN comes from our Japanese colleague here. Okay. Okay, so as I said, the fractional quantum state is where that you can find a lot of the anyonic states. It's at the abelian anyon as well as non-abelian anyon. There are a lot of them are there, and especially if you go for the so-called Jane series, which actually comes into the creating composite fermions by just kind of flux attachment, then you can get this Landau levels of the quantum Hall effect of this composite fermion, which can explain the most of the odd denominator quantum Hall states one can get. It's actually, if you have the quasiparticle on those kind of states, it's been believed to be abelian anyon. And some of the states, which actually not showing here clearly, somewhere that if you go there here, there carefully and zoom in there, there are kind of in this old work, there's barely the appearance of appearing 5F state. These are the again that pairing of this composite fermion the condensed into the kind of superconducting state, and this is state the quasiparticle excitation of this even denominator state is considered as an non-abelian anyonic states. While the theory, the proposal was there, experimental proof of this the abelian anyons, the anyonics of the any quasiparticle requires some of the experiments that kind of really show that. And one way that people realize to show this type of the anyonic physics is just kind of pushing this interferometry and just look at the interference pattern of this interferometer. It can tell us kind of those kind of things. And quite early on, starting from early 2000s, and that several groups, especially multi-Hyperlum's group, which actually made several seminar work on this field, as well as many other groups actually follow, try to kind of build up this interferometry efforts. It has been hard, however, as I will touch upon a little bit of few important aspects that why it has been hard in a moment. But it takes about kind of indeed 20 years after hard work of the multiple group to start to see that at least a glimpse of the braiding effect of the anyons that comes up. It comes up from the abelian anyon for the most of time, although there's some of the efforts in non-abelian anyons is there. But the 2020 is a probably big year for just presenting the experimental evidence of the anyon braiding. It comes from the two groups. The first group is the Michael Manfred's group at the Purdue. And basically, this group shows finally that making this the Fabry-Perot interferometry. So anyone doesn't know about this the Fabry-Perot interferometry is something. Where is my mouse? Yeah, I think okay. So I see that. Okay, so you travel through the different monitors. Okay, let me see what I can get. Okay, got it. Right. So this is a problem with this guy. Okay. So here is you have the two-dimensional electron gas and put down this all the gate structures on the top, which actually deplete the underneath and form this kind of circuits in this way. You can see that this is a QPC, which is a very important piece, where the quantum states are flowing through this edge of the sample and edge is defined by this gate. So going through here, this first QPC, and either it's scattering off or that it is kind of getting into this cavity, and this is second QPC. Again, the partition the wave functions, and basically out of this, you can get this interference out. And more important part is that this interference pattern start to show some of this the phase jump. And this phase jump is related with this anyon number occupation changes. And analyzing this phase step, they announced that indeed this is evidence of the abelian anyon braiding, especially 1/3 of the quasiparticles they are seeing here. About the same time, there's other experiments was done by the Favre's group in France. Actually, this is a beautiful experiment also showing that in these cases, they just kind of make the anyon version of the home and their experiments, meaning that two anyons comes in, collide at the QPC and scatter up. And just kind of analyzing this scattering properties, scattering statistics, they can demonstrate indeed the kind of braiding phase of the anyons on these two experiments. And basically, this defined that first two experimental evidences showing that indeed one can see that the braiding phase of this particle. Of course, kind of shortly after follow through, that one of the success of this experiment to take the 20 years. In fact, you have to really fight with this so-called Coulomb dominant effect versus that the anionic phase, which actually I'm going to explain in a moment. But one important aspect of here is basically bring the gate very close by to the under the 2-deck without sacrificing of the electron interaction too much. You can still kind of suppress long-range Coulomb interactions in such a way, and that's kind of one of the essential part. Of course, this type of things can be also copied in graphene. Not surprisingly, the people working in the two-dimensional electron materials like me and few other groups try to quickly just kind of come up with these very similar device structures, meaning that graphene encapsulated with the boron nitride, put the graphite gates at top and bottom. Graphene mobility is approaching to the millions or even more than million. It's basically limited by the size of the sample. So you can quickly see that the quality of the electron gas is approaching the best quality of gallium arsenide. Furthermore, if you just choose bilayer graphene, for example, you can get the even denominator states where that non-abelian anyon can be pops up, can be realized in bilayer graphene rather strongly because the gap there involved is much larger than gallium arsenide. So there's a hope that we can just realize very similar physics that has been done in gallium arsenide and graphene. Here's a kind of device fabrication steps briefly summarized, and device itself. You can see that we use this top and bottom gates made of the graphite, which actually enhance the electron mobility even further. Top gate is partitioned into kind of many different segments, and this will serve as a gate to control these quantum edge states through there. And some of the gate need to be just connected by so-called air bridges, which actually has been developed by Moti Bloom's group for some time. Just basically make the structures. In the end, basically you get the very similar structures, right? Here's why our QPC, 2 QPC, and this is the green part is our that cavity where that the electrons following through this quantum or edge states will just circulating a couple of times before it leaves, and pick up this ion bomb, phase out of it, and by just kind of controlling the magnetic field, for example, or the gate voltages, you can see that the downstream of the conductance measurement will start oscillating, and this oscillation is really related ion bomb phase and contains information about the potential exchanges of this particle. So we know that properly designed graphene quantum Hall interferometry seems to work, and then not only me, that my group and few other groups actually about similar time demonstrating that at least graphene-based this quantum interferometry work. Okay, so yeah. No, actually, the gate voltage change is actually good question. Let me just kind of explain that with this plot, this one. So let me just kind of step back. It's a good question. So how that interferometry actually work and what we are chasing? I think that's kind of good things we can show. So what is ion bomb effect? It's actually kind of surprising. I don't know if and that Bohm come up with this idea. 1959. It's actually more than 30 years after the quantum mechanics, although this is kind of something kind of from the beginning comes up rather quickly. So it was kind of interesting to see that in this seminar paper, they just show that indeed applying the magnetic field into the discharged particle path, and as long as you just can make this interferometry, you will see that there's a constructive and destructive interference can be modulated by the underlying magnetic field, right? So that's kind of something we learned from the quantum mechanics. There are many different ways of the experimental realization. One thing that related with our discussion is this electron, the iron bomb effect, which was realized into this metal ring. This is done in the IBM in the 80s. You can see that it was realized experimentally in the 80s. So once that you know how to create such a small ring, I think this ring diameter is something like 100 nanometer, and that ranges. And that the width of this line is about a few tens of nanometer. So it's only can be made by the electron beam lithography. And that's about the time that people just kind of develop the electron lithography, right? And this is made of the gold, but the important part is applying the magnetic field and simply measure the resistance across this the gold ring, right? And the idea is simple, that when the electron is coming in, that kind of make this both way that's come back, right? If this the flux here is whether flux quantiles the integer numbers or half integer numbers, then you can get this the constructive destructive interference make this oscillation. So basically measuring the resistance or conductance of this ring, that we can detect this oscillation. That's kind of the part, right? So you can just imagine that, all right, so when it goes with the quantum Hall, we can just do the same thing, right? So I'll just show you that this, you know, somehow I don't like this. Okay, yeah. So once you get into the, let me not use this pointer, but I will just use this as a pointer, yeah. So, no, I think that's okay. Yes, I think, yeah. So once, I think this one probably is okay. Don't worry, yeah. So once you get this kind of islands there, right? And then you can just ask that what is the around bomb flux getting to this island? That is basically defined the interference pattern, right? And there are two things we can change. Of course, changing magnetic field is one way that you can just kind of get this flux content changes, but also you can just kind of change the area of this island. Note that this area can be tuned by the gate voltages, especially this side gate that we call is a plunger gate. Applying the voltage on this plunger gate, I can change this area of this island, right? So both the magnetic field and applying this plunger gate, which actually changes this area, will just tune the the transmission coefficient across this two the QPC, because the phase we are getting, the path through this QPC is dictated by the iron bomb phase in this our experiment. So that's basically the idea that work it out, right? So usual experiment is getting this kind of interferometry and applying the magnetic field, and both changing the magnetic field and gate voltages, right? And see that where is the interference maximum or minimum is flowing through, and you will see that basically this type of the transmission coefficient changes. Of course, in the reality, we cannot tune this area too widely, right? So actually experiment, we are just kind of doing that is probably some small corner of this phase diagram, right? So that's kind of where that we are just kind of getting there. They typically tune the magnetic field and gate voltage. So you will see a lot of experiments, and already you saw that some of the interference measurement I showed you, right? Seeing this magnetic field and gate voltage changes, the stripes comes down, and this stripe is nothing but maximum or the minimum of this interference pattern is flowing in the kind of directions. So that's kind of experiment you're going to see a lot of times, right? For example, this type of the interferometer, we get those interference pattern that I showed you as a function of gate voltage, I guess, the change in magnetic field, the flow is flowing something like in that direction. And that's kind of evidence of the kind of interference, right? Why it has been hard for 20 years? I think that's kind of questions you may ask, right? If you go back to the original paper that Multi-high balloons or that Charlie Marcus and those kind of papers in done in say 10 years ago and 15 years ago, direction of this often this is called the pajama plot, by the way. So look like the pajama shapes of the design. This direction is not in this direction, but often it can be vertical or sometimes even opposite direction, which actually completely kind of against of this description, right? And the reason that why this is harder is following. There's one important assumption I made kind of when I draw this one. look at this, compare with your gold, the rings versus this one. This is basically the gold. We just carve out this the path, and then inside is basically kind of complete insulator, right? Here, that inside of here is quantum Hall insulator, right? And the path is defined in this way. But as soon as once you change the magnetic field, in quantum Hall state, you have to plug in the one flux quanta into the system. And with the flux quanta, in fact, we have to put the one charges in there, right? And if I just throw in the one charges into the system, that's basically what quantum Hall dictated. If this flow circuitry or that kind of area got changing, right? But then effect of the increasing magnetic field has a two effect. One is changing your atom phase, but also changing the area, right? So this is actually complication. And you have to prevent just kind of the area got changes by just increasing the magnetic field, and only get this area fixed and the magnetic field increase. And that's kind of where you have to engineer that your electrostatic in the right way, such to prevent this one. So it can, coming this way, basically takes about 20 years, right? So in the graphene interferometer, we certainly have the one very strong advantages. One advantage here is that we have the yes, Dimitri. Yeah. 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 That's right. Yeah. Well, graphene that we learned from the gallium arsenide, we just studied after gallium arsenide demonstrated. So we know that is important. So you have to put the gate in about the right distances. So not too far, but not too close, such that fractional quantum state can be still kind of preside, right? Yeah. That's also the issues. I think you will see that. I think actually this is kind of good way to demonstrating. You can see that in this, let me just challenge this once more. Yeah, it works. Sometimes works, sometimes not working, like my device. Right. So we carve it down, and of course this channel is important. A more important part is basically this QPC that we create in this way. QPC quality is kind of very important. I can just show you here that QPC by just tuning the QPC gate, which is basically this guy, and look at this the transmission of the QPC. Where there is the kind of integer is well defined, but in between there is kind of fluctuations there, and that's probably some of this the disorders and that sitting that near the QPC will create this type of the fluctuation, and that's something that usually not too good things you want to have, right? So we made actually quite a progress in after first version, and the second version of the device actually we instead of we just tune the QPC gate separately, we just basically fixed all the QPC gate, but then everything is basically fixed when we just do the experiment. We have now the separate QPC gate, which actually overhang again. So this is basically overhang bridges that are sitting on the QPC area. So changing this gate through the air, which is the best dielectric you can just think about, vacuum, right? And then basically nothing is tuned except that QPC area density is changing by the QPC to QPC gate that we just put up there. And that immediately provide us the much cleaner data, much cleaner sample, and can well-behaved devices. And I'm going to discuss a little bit about what we get out of this type of device. So the first thing that we get this device is that we can see that kind of various controls the experiment is possible. For example, that instead of the one edge state, if I have the two edge states kind of the turning around inside of this QPC, inside of this cavity, you can see that by just tuning the QPC gate, we can partition either inner or the outer the quantum edges there. And you can see that if I just record the interference from the outer edge versus inner interference, basically you start to see that oscillation is there, the interference there both, but the behavior is different. For example, inner quantum edges, basically oscillation seems more regular. Outer quantum edges, the oscillation is a little bit irregular at the fixed magnetic field, right? It becomes clear that when we start kind of change the magnetic field, you can see that in these cases, in the quantum edges, the interference, we see that this there's not much of the jump, and that constant phase is coming down. Certainly outer quantum edges, what we are seeing is there's a series of the phase jump appears in this channel, in this interference case. I'm not going to discuss all the detail, but if you just kind of do careful analysis, it turns out this phase jump is related with, in fact, in this particular case, since we are just kind of doing the partition, the outer interface, outer edges, and inner edges, in a sense, isolated. So you can view that this is kind of the quantum dot, this ring-shaped quantum dot, reside inside, right? Every time this quantum dot is charged up, that will just kind of push it outer gates, outer edge state a little bit, and that appears as basically this jump, right? So integer quantum Hall effect cases, you can also create this jump or phase changes by just kind of creating some of the charge centers there. So I think that's kind of something new, something that we show that, well, we have the kind of quite good control. So once that we have this type of the data, we had actually high hope that we can probably reproduce what has been seen in gallium arsenide, at least in the abelian cases that we can just think about. So crank up the magnetic field even further, something like the 14 Tesla or 13 Tesla in that kind of level. This type of the interferometer start to develop a lot of the fractions, more important, including that 1/3 and the 4/3. I think these are kind of too strong. The fractional quantum state, although this is abelian, basically this is kind of good starting point. We can see whether compare with the integer quantum or what type of the different interference we will have. Okay, so what do you expect to see? So let me just go back to see that what is the difference that we expect between the integer and the fractional quantum state interference. So this is a simplified pictures of the interferometry. Again, as I said, area can be controlled by this plunger gate, right? And I'm monitoring that downstream of the conductance measurement to see the transmission coefficient changes, right? First of all, that when we get from the integer to the fraction, there are two things get changes in the interference. First thing is charge, especially the quasiparticle, which actually floating around in this the quantum edges, their charge got changes. Integer, of course, is electron, so it's electron charges. However, in fraction, all the fractional quantum state is one important marker is their quasiparticle is also fractionalized, right? 1/3 fractional quantum state, or the denominator with the 3 fractional quantum state, their fractional charge, the anyons, quasiparticles fractional charge is 1/3. Therefore, that is a fractional charges. And why that's important? Because if you just go back to the Aron-Bohm effect, that the phase we will get, or the flux that we will get, is basically related with the phase coming from the flux is related with the charges. So if it is fractionalized, we should be able to detect the Aron-Bohm phase got changes. But on the top of that, another important part is basically now when the localized charges they're sitting inside of the dot, for example, and then when I have the another quasiparticle is kind of circulating around to pick up this Aron-Bohm phase, you can start to see that, of course, because of this, the getting this Aron-Bohm phase out of it, you have to exchanges these particle positions, and that will start kind of pick up so-called exchange angles as well, exchange phase coming from anyon braiding. And that's basically, that's essential part of this, why the people are working on the quantum Hall interferometer to detect anyon braiding phase, right? Because that's kind of the way that when we now detect this, the interference phase, there's two components. One is coming from the Aron-Bohm phase, which also contains this fractional charge effect, right? So in other words, basically your Aron-Bohm phase that along the magnetic oscillation becomes 3 times faster or 3 times slower, right? And then the fractional statistics also plays a role in changing this the phases. In fact, if you go back to the Manfras data, that's kind of exactly they are seeing, right? So first of all, that there's this plasma plot as a function of the plunger gate and the magnetic field flowing the right direction, and the slope will just kind of give you the information about what is the fractionalized charges, right? But then there's this phase jump appears, right? And this phase jump is related with that accidentally there is a population of this the quasiparticles sitting there. that will give you the phase jump. And you analyze this phase jump, it requires a bit of the electrostatic consideration. But if you just do it right, you will see that this phase jump is related with the kind of 120 degree, which is expected from this anyon braiding into the system, right? Okay, so can we actually get this into our graphene device? So once we get this kind of the large kind of well-defined fraction, of course, we just kind of park there and kind of try to measure this interference signal. Very initial report is very disappointing. Although this device shows a beautiful integer, when it goes to fraction, it's completely garbage. We just kind of showing here the signal that we fix everything, including magnetic field, the gates, and thing. It's only time left, right? What you get is that basically the signal of our interferometer is not stable enough. Over the time, it's just basically fluctuating, right? And time sequence we have is about something like a few tens of seconds. So we thought, okay, so at least I thought, yeah, you know, I think somehow this device is not yet kind of optimal. So maybe we have to redesign or make the kind of make another device and just to do it. I think this is the best we can do. Lowest temperature we can get, 12 Tesla. So we thought, all right, I think that's it. But then Tom just kind of noticed that, yeah, it looked like the kind of garbage is a kind of random telegraph noises sets in with some reasons. But at least you can see that there's only 3 levels shows up, right? It is a telegraph noise, but not a 2 state, not a 4 states. It's a 3 states. Why 3, right? Of course, maximally hopeful that if indeed there is the anyon that kind of pops it, and this is kind of really anyon jumped in, then create this some of this jumping into this signal. Of course, any anyon jump in, that we expect to see the 120 degrees phase shift. So no matter how many anyon jump in, basically we only get this kind of 3 different type of the phase coming from an anyon jump in. Therefore, we will probably have this n mode of the 3 when n is the anyon numbers of the 120 degrees of the phase shift. Okay, well, that's a maximally hopeful stories, right? I think, but out of this noisy data claim, that is kind of really hard. But then the next thought is, all right, we fix everything here. So what if we start to change something, right? For example, we can just change the plunger gate, right? See how that this got the random noise got changes. And that's where that kind of really surprise comes in. So experiment we did is basically at the plunger gate, we get this 3 different set of the values that reasonably well separated. But now change in plunger gate and repeat this measurement and just make the histogram and plot it out as that's functional plunger gate. And that's basically the signal we have, right? And once when see this one, it was kind of quite surprising. First of all, that those kind of 3 values that we had, in fact, as you change the plunger gate, there is 3 pieces of the sinusoidal curves comes around. And the separation of the phase separation of this size 3 sinusoidal curve is exactly 120 degrees, right? Clearly tells us that indeed this actually dictated that stories of that about this the interference signal with 120 degrees of separation of the this phase, right? So when we saw this one, that it's clear that it's not only us think about this one. In fact, many years the theorists already discuss about these possibilities. That possibility is basically when you have this random occupation of this anyon sits into the quantum dots, you will see that these 3 branches of the interference pattern will randomly switches in between as the anyon jumping. Kind of that's kind of basically another way to can prove this the anyon braiding effects as you shown here, right? Okay, so that's kind of interesting part. How about the AB oscillations and charges, right? I just told you that if for the integer, same device by the integer filling, that we get this nice, the so-called pajama plot, magnetic field versus gate voltage, the gate voltages. And this slope will give us that information about the information about the this slope will give you information about this quantum the dots, as well as that charges that responsible for this one. So to get this type of the experiments, by the way, that over this long time of scanning, that my interferometer should be absolutely stable, something like this. If you just kind of, instead of changing magnetic field, I change the time, everything is just kind of stable, right? Of course, this type of experiment is miserably failed for us for integers, the fractions, because as I said, fraction basically every tens of seconds that we have this random jumps comes in, right? So if I just look at the same condition, 12 Tesla at the kind of fraction, you get this type of this smearing out, right? If you just look at the couple of the line cut, it's nothing but basically the sinusoid curve is a randomly shift in this the phases, but the phase shift is about 120 degrees. But there's a way, a clever way, actually we can just do that. The same data that here, if I just make this a histogram and plot it out in terms of the plunger gate voltage, this is kind of what I showed you before, right? But this data is fixed at the 12 Tesla. So now you take this data, changing the magnetic field, and see that how this phases got evolved. And you can see that if you just look at carefully, the phase is in fact evolved with a certain distance, certain ranges. And if you measure that the slope, and the slope is precisely 1/3 of the slope that what we expected from the AB oscillation, telling us that the charge, the fractional charge involved in this the interference pattern is again 1/3 as expected, right? So that's basically kind of the observation we had, and we got quite kind of excited about. At least this, we thought it was kind of complete garbages and random telegraph noise, but noise contains some signal, and this we could extract. Yes, yeah. I have a question. Yeah. Yeah. Yeah, so you kind of can I just increase the visibilities of this amplitude? Yes, indeed. We can just kind of tune our QPC parameters, and that the best parameter is about 0.5, 0.5. I think that's kind of the, in terms of the theoretically maximum visibilities it gets in. Yes, I think good. That's also a good point. That's kind of related. I don't have the slide for that, but I can show you later if you are interested. Of course, that's not enough, and even there is not the kind of visibility one. That phase coherence length is an issue. So that's why you have to go to the low enough temperature. As you go to the low enough temperature, then phase length, coherence length becomes bigger, larger. But anyway, so there are kind of many other factors, including these temperature issues. Yeah. Right. I think it's only kind of 10%, so it's not necessarily too large. But again, if you go back to gallium arsenide in here, I think it's a very difficult to get the visibility as one in many aspects. Right. So we're happy at least showing that this is a kind of the statistical way that we can just kind of present this one. So we just wrote a paper and put it into the archive. I think it was about 3 or 4 months ago. And then after 2 days after this, we put this paper in the archive. I got an email from Shankar Dasama. And anyone know the Shankar, that if you get the email from the Shankar, you can immediately realize, even before read the email, gee, I did something wrong here, right? And probably I didn't cite his paper correctly or something, right? But then it's interesting that Shankar pointed out that, I think this is nice work and good, but I think you're overclaiming something. And what he's saying is, it's only not me, but others in the field as well. And what he's saying is, I think what you're saying is not seeing the exchange statistics or the braiding angle, but what you're seeing is basically double of that, right? An argument that which actually he wrote together with Nick Reed is following, right? If you just kind of read this paper, essential part is when you say the exchange is basically changing the particle indices, right? That is correspond to basically kind of rotating 180 degrees, right? But when we just do the interference experiment, we just kind of one particle is kind of flowing through that pick up this bone phases out, right? And so we thought, all right, so this is exchange, but this is a braiding or double exchanges. You can say that. But he pointed out, no, this is not braiding. And he just pointed out that there is the 1920s mathematical paper, mathematician actually defined braiding is basically the same as exchanges. What you do is double exchanging, right? Okay, that's a nomenclatures. However, that's a definition, but there's actually more important part, which actually I completely agree, is because of this, basically experimentally we can measure only twice of the exchange phases, right? What does that mean is that because of this effect of the two, we cannot, there's always sign ambiguity on this the braiding phases. In other words, basically in these experiments, we cannot distinguish the electron versus the fermion versus boson. Likewise, basically this sign ambiguity is still in there in this experiment, as well as gallium arsenide, by the way, right? So we happily admit that, and then we changed the title, right? But then that we found it yet around the time interesting preprint that theoretical proposals done by the Steve Kiverson and Murthy. And then the idea is kind of interesting. The idea is if somehow in this interferometry, if you put the quantum dots at the QPC, but this quantum dot is, or quantum antidot, is basically the dot for the anyon occupation. And then one can get into interesting regime. This is the following way, right? So if this dot is empty, but then when anyon is coming here and just kind of cross this QPC, well, you just kind of tunnel through the antidots arriving the other way. In terms of the exchanges, the exchanges angle, you just don't make the difference between just kind of what we just did without QPC, without this quantum dot. But it's when there's the anyon is already occupied in the dot, when the particle comes in, there's a kind of cooperative tunneling process is happening. When this particle occupies the quantum dots kind of getting out, and the particle from the edge state to jump into the QPC, the quantum dot, and when this particle comes back, original position like this, and that's kind of precisely the situation. You just replace the exchanges two anyons in their positions, right? So with this argument, in fact, if you just compare with this kind of dot occupied and not occupied, basically you get additional the exchange phases, right, coming from real exchanges, right? So the proposal is if you have this quantum dots and occupied and unoccupied cases, comparing the phases, you will see the phase shift of 60 degrees or equivalent to 180 degrees. That's basically a theoretical proposal, right? Well, you may see that this is a crazy experiment, right? We barely make this QPC work, that putting the another dots in there is rather crazy. However, nature is kind enough that allows us that situation. I told you that we can make this QPC with that kind of connections over the top. If you just change the QPC gates on on, fix everything, we often start to see that there is that QPC transmission is kind of fluctuating quite a bit. But if you just zoom in the fluctuating area carefully, right, this will look like the kind of rather sharp resonances. And especially if you just change the source drain bias voltage now and changing this QPC gate, you can see the series of this kind of diamond elongate shapes. Anyone work on this quantum dot, it look like this, something like this, some kind of tunneling process through happen to the quantum dots area, right? Quantum dot stability diagram look like shapes appears. So now if we just really kind of believe that this might be related with this quantum dot formation onto this 1/3 QPC states, we can do the following experiments, right? We can just kind of choose my gate voltage is here versus there, okay, here versus here, right? Across the one of this resonance state, and surely one side is either occupied and unoccupied, and the other side will be the other way around, right? So comparing this phase could be kind of interesting. Indeed, with interference pattern we are getting, these are 3 branches we are getting, right? If you just kind of look at this, exactly across here, there's a phase shift of 60 degrees or 180 degrees equivalently, starter shows up, and we are distinguished between at least kind of the braiding cases here, right? So I think that's kind of where it is kind of quite interesting. Now we are not only seeing that double braiding, but even just braiding effect by just carefully control across this accidentally formed quantum dot, but at least this is one step forward, which has not been seen. Okay, good. Well, this is probably at this point where we are, right? But what is the next thing? So at least I'm sure that this abelian anyon, I think that proving that, or deeper states, I think there are kind of still quite of things. But eventually, the direction we want to go is, can we just do this in a non-abelian anyon, right? There is the theoretical proposal, what we expect, and that in this case, you have to make that this double fabric parrot type of the devices. There are already some previous efforts done in the gallium arsenide start to show somewhat noisy but tantalizing experimental evidences. So there has been some discussions. Now just kind of pushing this type of the physics we are just getting into even denominator states, and that's kind of something that kind of direction to go. And this is kind of summary that I just mentioned, and then outlook that of course next one is going to the even denominator states, but also more importantly that we can just put another gate and create this dot inside of our interferometer, so not anymore of the accidental anyon jumping in, that we can just electrostatically control this anyon population. So that's kind of some of the directions to go. Okay, how much time do I have, Dimitri? 10 minutes. Okay, so that's it. Probably a little bit short, but barely enough that kind of I can move on to the next part that I just mentioned. So the next part I will just kind of go a little bit faster, but at least kind of give you some flavor. So second part is now the other platform, right? Kind of superconductor combined with topological system. Here that I'm going to discuss about the real topological insulator with the surface state of the real topological insulator with the superconductor combination. A different set of the collaborators and students, and the Tom is here, but it's more important that Junyoung Park, that postdoc in my group, is basically leading these efforts with many people in combination with, again, Amir is here. But here the more important person is the Bob Carver and the postdoc here, who provide us the extremely high quality of the topological insulator that I'm going to describe in a moment. So idea, first of all, that before doing that, there's the important part. When I say that now the flux quanta in this one, because I'm dealing with a superconductor, the superconducting flux quanta, which means the electron charge E should be changed to the 2E, right? So that's kind of one sign. But the idea itself is rather straightforward, and it's dated back to the almost first paper that related with this topological, proximitized topological insulator, where that this original proposal of the Liang, the Fu and Kane proposal, where that you proximitize that surface state of the topological insulator with superconductor, even with SA superconductor. And along this, Josephson-Wick link made of the topological insulator, there is the one-dimensional, the propagating Majorana mode can be exist there. And in fact, this original paper was already kind of pushing it up to the far. You can create this kind of 3-segment to the Josephson junctions, and that kind of put in the right phases. You can actually trap those kind of Majorana into this triangular point, the vertex point, and it appears as it is Majorana, but it appears as in Josephson junction languages, the Josephson vortex is basically formed at the point, right? And depends on to how you phase bias onto this 3 superconductor, you can just move around or create this, creating or just kind of manipulating this Majorana. Especially, again, the same paper, it was a very amazing paper that they already think about kind of getting into this the tri-junctions and phase bias in different way. You can create this Majorana, diffuse the Majorana, move around the Majorana, and detect and initialize. Many ideas already there, right? For the experimentalists, in some sense, therefore, just realizing this system, I think it's again that almost getting 20 years old kind of idea, right? What has been the problem? There has been a lot of efforts, of course, in this direction. And then a few examples that I can show you here, that mostly that using the different type of the conductor platform or superconductor platform to realize those kind of Majoranas and try to kind of find out the evidence of the Majorana. Then a lot of the problem here is, of course, the material quality, material processing has been quite of issues, especially this 3D topological insulator, but also what to measure, how to demonstrate the braiding, how to just kind of do that, and those kind of things has been some issues. Although there is some interesting observations, such as nodal lifting of the fractional pattern, or that the missing of the Shapiro steps, odd period of the Shapiro steps, and those kind of things there. there's other interpretation is possible for there. So there is again that smoking evidence is still kind of lacking, I would say, right? What has been changing this, the thing is, okay, of course, again, the quality of the material becomes better, right? The experiments we actually realized on is this amazing crystal we obtained from the Bob Carver's group, where that they just make the compensation doping to create this so-called compensation doping of the BSTS, which is a bismuth antimony tellurium sulfide, doped by the tin. By just tuning this one really carefully, they really make the bulk insulating. That if you measure the residual carrier in the bulk is 10 to the 14 per cubic centimeters, right? That's actually levels of the what you can get the refined silicon, intrinsic silicon. So that's amazing. So that's kind of allows us that make sure that you really suppress the bulk conductions there. Followed by that something that my group added there is basically process this one into the really controlled environments. So this crystal is cleaved. It is a reasonably air sensitive sample. We cleave that in the glow box with core stages. We move the crystals into the UHV evaporation chamber, evaporate the tellurium on the surface to protect it completely. And then we just do the typical processing afterward. But then we bring it back, and right before the superconducting evaporation, we then remove this surface, the passivating tellurium layer, put down the superconductors on the top, and all of these things actually is required to provide us the rather pristine device structures. And device, the structures we also worked on is a little bit kind of different device structures than others worked on. It is more like the Covino device structures, which means that we have the inner contact and surrounding outer contact. And weak link has some this annular shapes and kind of periodic boundary condition. In this way, that we get rid of all the edges, right? Except that all this, the boundary of the sample is basically bounded with the superconductor. Already in this junction, you can imagine that when you apply biased magnetic field, apply the magnetic field, and then those magnetic field will create this kind of the vortices. In this center of the vortex, you can imagine that there's Majoranas there, according to the theory is right. And sending the current, eventually this the vortex start moves around, right? If the vortex start can moves around, and that will just give us kind of immediate kind of sense of the winding of the Majorana. In fact, there has been some theoretical approaches, theorists, the discussions how to just winding around, what is the signature, you may see that. There's kind of further. This tri-junction I mentioned is very important that not only braiding, but you have to fuse them or the creating them. And the combining this, Covino device with the tri-junctions, you can define that you can make those kind of, the Junyoung actually often call this is a Pokeball device. And the older generation, I don't know what is Pokeball, but certainly anyone that ages 30 and below probably know about the Pokeball. So this type of the device allows that, in fact, that by controlling this Josephson coupling here as a phase bias, in principle, you can create this combination with the tri-junction with the Covino device is possible, right? So I'm going to show you that kind of very first steps of the kind of doing that, what we actually getting out of this. So first of all, device fabrication, I already mentioned that we have to just do the encapsulations and doing that. And of course, Covino device, we have to put this inner rings, the contact. So you have to make, again, the bridge device structures showing something like here, this Covino device and contact. There's a Covino device with a square shape. And doing that, you have to choose your superconductor right and processing it right. But end of the day, we get the fairly good contacts, the contact transparency that we just estimate is about 70% or above. And then junction quality is high enough such that we can expect something interesting happen. Right. So before we get into more complicated things, I can show you some already interesting and fun aspect we are seeing. So here is a Covino device, a circular Covino device, and simply we measure the supercurrents through that and apply the magnetic field and how the critical current can modulate by the magnetic field. This is a Fractional pattern, right? However, you can see that if the outer ring is large enough, right? Applying the magnetic field, you will not just kind of easily put the fields in there, right? Because you have to cross that the superconductor, which is now even has a really higher the critical field. So this experiment is actually done very expensive way. Every time you change the field, we have to warm up the device above the superconducting transitions and apply the magnetic field and cool it down. This is basically field cool type of the experiments every time. So every magnetic field you can see is very expensive. We have to go up and down, right? So then you can see that, first of all, data looks kind of pixelated here, right? So you can imagine that, oh no, this guy is actually probably every several milli Tesla, you go up and just to do that and plot it out in the 2D plot as if that you just extend it by this mechanism. That's not the case. In fact, this resolution, I think there is more than I think 100 points or kind of level of 100 points. But why data is kind of pixelated here? But you can see that the pixelated, that is about the width, twice width of the kind of first, the dark strips you are seeing. First, the dark strip is where that we got the zero resistance. In other words, that's basically true superconducting states, right? Well, eventually that going the really high magnetic field, we will see that the HC2 is there, but I'm not going to I'm showing there, right? This means that after this dark strip, any finite magnetic field tend to make that this is non-superconducting, right? But if you just think about a little bit, that is kind of expected, right? Because under the magnetic field, that once you just kind of apply the magnetic field, that the first magnetic field, until that you can create this one flux quanta, the Josephson, until that you create the vortices, the field cannot be get in there, and this is basically my Meissner state of this Josephson junction. But after that, that I can create only integer number of the vortices in there because of the outer side of superconductor is still superconducting, right? So what you see here is basically above this dark strip ranges, I start to kind of populate the integer vortices. But lesson we are learning is as soon as there's a vortices, applying the current, vortex can happily moves around. And you want to know about the superconductor, moving vortice will just dissipate, right? So there's a voltage comes up. That's kind of what you're seeing, right? So, and that this stripe shape appears because of that, yeah, that's every time we see that one vortex and two vortex comes in, that kind of device behaves kind of somewhat different way. How can I make sure that this is really the case? We just kind of show that now this is a square Corbino device. And you see that that effect is kind of rather different, right? So dark strip here is the same, but now I have dark strip here, dark strip there, and dark strip there, dark strip there. Let's ignore this for now, right? And you can count the numbers. How many vortices I have? 1, 2, 3, 4, right? So once I get the 4 vortices, I get the kind of higher critical currents. Why is that? Because I have the 4 corner. If I see that the vortices in this corner is happily pin those kind of vortices. Therefore, that there's a little bit more vigilant, right? So that's kind of why you get the high kind of critical current. All this story is nothing special. It's basically as you expected. If you have a Corbino device, this is kind of what is expected, right? What is it? Kind of next thing is now we cool down the lower temperature, but my story is completely breakdown, right? I got the kind of the critical current everywhere, right? Although I think there's still kind of 2, 4, and 6, 8, and there's an interesting pattern, but the first thing is a critical current is everywhere. Why is that? Because it's a low enough temperature. There are, of course, my device, although we try our best, it's not that kind of cleanest annual ring, which means there are a lot of this kind of inhomogeneity and disorders around the ring. Low enough temperature, basically vortex start to lose its thermal energy. They can pin any of the small defects we have inside in the Corbino, and that's why we get this one. But nevertheless, I think this even out the even kind of number of the effect is kind of rather strong, and as you see here. Okay, we can just kind of go through all the kind of detail we can analyze, but let me just skip that part. But on the top of that, we start to see some interesting part. We see that if you just compare with the positive and negative the current, and especially positive and negative field side, there is a clear evidence of the so-called Josephson diode effect. In other words, positive and negative side of the current, critical current is not the same, right? Though once you map it B and negative B with the I and the negative I, they are matching. So we know that this is a kind of clear signal of Josephson diode effect. Seeing the Josephson diode effect per se is nothing too surprising because time reversal symmetry is broken by magnetic field. Inside and outside the Josephson device, basically source and drain configuration is kind of different, right? So inversion symmetry is broken there, right? So, okay, so those two symmetries are broken. Josephson effect itself not surprising. What surprises us is, in fact, this Josephson diode effect polarity is got changes with the magnetic field, right? Especially how many flux quantas in there. Once we compute this, the Josephson, the diode effect efficiency or the polarity, it actually switches back and forth every time. So I just kind of change the magnetic field, right? Magnetic flux. But if you just look at carefully, it is actually changing with the twice of the flux quanta. In other words, the negative and positive Josephson diode effect is related with whether I have an even number or odd number of the Josephson the vortices in there. In other words, it depends on to the even and odd number of the Majoranas in the system. It actually appears in for the robustly doesn't depend on to the whether it's a square or the circle, it's a triangle, right? So those kind of effect of this Josephson diode effect is kind of is there. In other words, there is a kind of clearly 4 pi of the periodicity of the flux that we are having here. In fact, this is again that's something that theorists expected because of the number of the vortices, number of the Majoranas actually changing the boundary conditions onto the Scobino devices. So that having the even number and odd number of this Majorana will just kind of change into boundary conditions, which actually relate with this diode effect that we are seeing. So that's kind of another kind of rather robust evidence that indeed kind of we are seeing that kind of number of the Majorana or the parity of the Majorana actually do matter. Right, so that's kind of the part. Where we are going. This one that of course showing that only kind of the number of the Majorana matters. Eventually, we want to show that whether indeed can you just kind of make the braiding, and then can you measure it, and can you fuse it, and just detect this one. And for this one, basically, we need the kind of tri-junctions, right? For example, if you have the one slits like this, and look at the Fractional pattern, right? You can see that according to the this interpretation, depends on to the way you park. Of course, there's no the lifting is there, but it's less important. More important part is where you just kind of park in this magnetic field. Basically, we know that what is the conditions of the situation of these vortices, and especially when the fusion is happening, these two vortices must kind of pass around. That condition is forcing by just kind of looking at this the Fractional pattern and just kind of detect this type of the effect. So one has to go to the higher frequencies of just doing the Shapiro-Stetto type of the measurement. So I think that's kind of the where we are. I don't have yet the presenting smoking gun evidence, except again that those kind of even out diode effect, or if you just look at this collision and non-collision cases, high order this Shapiro-Stetto is suppressed and non-suppressed. Actually, again, indirect evidence one can just kind of present. But nevertheless, I don't say that this is kind of really direct evidence yet. But what you see here is already kind of feeling like the very similar type of the idea that I present into the anyon braiding cases. We start to have the much more controllabilities of the dealing with this the anyons onto this system. Hopefully that allows us to kind of get into next steps, just kind of demonstrating this effect. So summing up, that at this point we just created Kobina style of the Josephson junctions of the 3D topological insulator. And main observation we have is clearly we are seeing that odd and even effects of the Josephson diodes there. And of course, the next step is can we actually really detect that kind of effect of the fusing of the Majorana, and can we actually do the more controllabilities? And of course, eventually we should go to the pokeball geometry with a lot of this phase biasing loop that we can precisely control the location of Josephson, the vortices in this system. All right, thank you very much. I'm slightly over time, but I hopefully it's
no problem.
Thank you.
Okay, thank you. Okay, I think the microphone, no, it works. It works, right? Yeah, okay. Yeah, so questions?
Thanks. Thank you very much for the very nice talk. About the first part, I was wondering, this telegraph noise that, sorry, nice noise that you,
Yeah.
what is the nature of that?
Yeah, that's right. So that's
Is it
that's yeah,
Quantum
that's
tunneling or something?
oh, I can give you the answer. That was not in our archive paper yet, but there is a reasons. Okay, good. That I can just show you this this slide first. So of course we are not the only one, and there's a kind of, I would say in this field is always kind of family business, family competition. There are two groups about the same time report very similar result. Or it's not same, but related results. The first group is here's that Yuval Ronen's group that my former postdoc, who actually was in the multi-Abrams group, teach us how to make the suspended gate air bridges and those kind of technique. And then now he went back to Weizmann, becomes he leading his lab, and of course on the way he smuggled all this making 2D material technologies in there. Look at his device; it's exactly the same device I showed you, right? Not surprising, right? Except that they made it with a bilayer graphene. The another result he's showing here in the left is basically Andre Young's group, another my former group members, I think, and then the QPC design and those kind of slightly different, but nevertheless they make the device and just to do the very similar thing. The stark difference of this one is the Weizmann group's result shows a really beautiful pajama plot with a right slope, so they can see that all right, there are kind of the fractionalized charges there, right? But there's no jump at all, right? So they don't see that this braiding phase thing or double braiding phase here, right? Andre Young's group showed the slope, and there's kind of some the phase jumps there, and if you just kind of do it, kind of again that what Michael Manfra style of this the analysis with capacitance coupling, they got about the right phases out, but their phase jump is much rare. I think it's every hours or something like this, every 10 minutes or something. So they cannot do the experiment that we did, right? So basically we can just do the statistical things. They unless that takes a few years, basically cannot do these experiments, right? So in a sense, we have the little bit efficient way to present in their way because of this the noise, that because of this random telegraph noise, it actually comes on much faster than these guys, right? So it is, in some sense, the blessing that we get a faster result. But then the question is why, right? What's the difference? And in fact, actually, we figured out that this experiment need to be on really low temperature, well-filtered the cryostats. So we borrow the cryostat from Amir, that one of the wet fridges. But this wet fridge has not enough cooling power, which means that the shielding we rely on is basically rely on the shielding that made about 100 millikelvin or something like this. Shield is there. Our sample is 20 millikelvin. Our shield is something like 700 millikelvin. Okay, so yeah, I forgot that it was 700. And yeah, it's probably still. So you can see that there is a shielding that sitting at higher temperature, and our sample is 20 millikelvin, right? And of course, that 700 millikelvin happily emits any of the IR photons there, right? Far IR photon. Can be absorbed and just can make this jump potentially. That was kind of some idea. Well, it sounds like okay, but how do I know? How do you know? Tom and James made these small cages finally. So put the samples and completely cage it out with a darken the inside. So basically block all this kind of 700 millikelvin photons, and then now they try to kind of put this sample into these cages, that all the jump is completely gone, right? So I think it was a kind of poorly prepared sample that create this jump, but that's kind of what we know. But we can actually turn this is our advantage now, right? Because then there's it has not been done yet. The experiment was ongoing. We can now just get plugged into the small antennas there. We can just kind of inject the kind of the photons of the whatever energies we want. We can potentially just kind of make the anyon jump in and jump out by just kind of controllable ways. So that's kind of one thing that we are trying to do. Yeah. So it was a bad fridges.
Yeah, but that's good. That's good.
Thanks.
And so now you keep the shield cold, but you controllably just inject.
That's the idea. We haven't actually demonstrated yet.
Yeah.
Yeah.
Okay, more questions? So I have, meanwhile, also questions. So you mentioned, so Yuval is using bilayer.
Yeah.
Andreas also using bilayer.
I'm sure that everybody is working on bilayer, including us now.
Right, and you in
Yeah.
single layer. Is there like, in terms of like quantum Hall effect, fractional quantum Hall, is there like a big difference or?
Yes, yeah, of course. You get only even denominator states in the bilayer graphene easily. I think I would say that for the single layer graphene, you have to go to the extremely high Landau level, which is very difficult to achieve. So the bilayer, therefore, is that if you want to go for the non-abelian anyon, this is really go for. Slight kind of annoying part of the bilayer is, of course, now bilayer quantum Hall states is sensitively changing with the displacement field. So ideally, you want to have the split gates or the top and bottom gates kind of matching, but that is rather difficult to make. So you have to work into the certain phase space carefully, but nevertheless, it should still kind of work it out. Yeah. I think that Alex has questions and that, yeah. Okay.
Hi, thank you for the nice talk. So in your first experiment you mentioned, so if I understood correctly, you have some kind of Fabry-Perot state here, and then you are probing the state of this Fabry-Perot cavity.
Yeah.
Okay, and so you are measuring the statistics of the occupation level of this
patient changes. Yeah.
Okay.
Yeah.
Did you try temperature measurements?
Oh yeah, of course. Yeah. So that's because I have to plug in the second topics, I have to cut it out quite a bit. But yeah, temperature dependence is something that you first want to see, right? Of course, the first of all, that the jump, all that visibility we are seeing do change with the temperature, as kind of pointed out, that phase equivalence kind of lengths kind of get involved. So visibility has got changes. But also you can see in the raw data, as you go to the higher temperature, not only amplitude is decreasing, when the visibility is decreasing, but the frequency got changes, right? So the frequency is related with the phase rate, the kind of jumping rate got changes. And you can see that as you go to the higher temperature, it becomes a rapid and more higher temperature in this direction. It's kind of going more rapid. And if you just kind of work it out, this one, more or like this one, the hopping rate of this annual hopping rate more or less follow this Efros-Shklovsky type of this variable range hopping type of thing. So which has been seen in the trap dynamics in the quantum Hall system, especially initially the integer quantum Hall system. So we believe somewhat similar things may goes on into this anyon traps we have in the system.
So it's more than just changing the population here. It's really changing.
Yeah. If you're interested in that direction, one can do more things, right? Also, when you change this gate voltages, especially where you are seeing the kind of plateau, you can also change the kind of the localized states numbers, right? In the center of the plateau, basically, we have the less of these traps. As you approach the edge of the plateau, there are more traps around, right? So you can see that how that distribution got changes, that switching rate got changes, and then you do see that there's a kind of dependence. The more important part is your Fourier transform of the noise spectrum, noise time sequences, and look at this spectrum, how that it got changes. And you see that the noise spectrum is 1 over f to the 1 over f square. 1 over f square is basically more of the Poissonic distributions. But that if you go to the 1 over f type of the things, that there's probably more multi-levels and multi-energy scale got involved, and those kind of things can be seen in the system. So you can just kind of do that. Again, kind of more complicated analysis can be possible here, right?
If I may.
Yeah.
Yeah, one more. Yep.
One more question. So your overhang bridge.
Yeah.
You can make them either, how do you say that, as working as a gate, or having no influence on the sample. Can you tune the height or?
We can just tune away, but we don't have to make it even, right? So I think you can tune the gate voltage in such that it does not kind of influence that underlying the electronic system as well. So having the overhanging gate, I think it bothers you that because it's somehow it's up there. Why are you asking that?
Because sometimes it's just overhanging to make the contact to the how to say that remote region.
Yeah.
And sometimes it's to use it as a gate. So
The gate and that gate and the contact is separate things. If you just look at these device structures, right? I think strictly that our role of this. So this one is overhang gate, but that one is basically the contact onto the central part. So the roles are different, right? So what you're saying is when this goes on, that it may actually cross into this channel region. So whether that they're affected. Okay, good. Yeah, that's a good point. It's another big problem because of that channel region is a rather deeper potentials. So overhang gates will gate a little bit probably, right? But that effect is much, relative effect is much weaker because the QPC region is where everything is basically shallowly controlled and small changes make the big differences. So it was kind of critically the tuning there. The overhang gate is still kind of effective. In the other kind of channel region, basically it was a deep trenches already. It's not necessarily kind of bigger problem. That's right. Yeah.
Also from my side, thank you very much for presenting these beautiful results. I have a naive question, but I have to take care how to word it. So for example, when you showed the variable range hopping, where does this occur in the overall interferometer, including the QPCs? I have this, I don't know how to word it correctly, that it's not too naive, or does it sound too naive, but where do you have this interaction of the anyons with the interferometer?
Yeah, that's a good point. Yeah,
this
that's
is
a
my
good point.
point.
Yeah, no, actually, that's oddly enough, that's the same questions that I got from the referees. You try to disguise. I don't know how to put in the word. Joking aside, I think Joe aside, there are actually many people ask us similar questions. It's a very common questions. Yeah, this is a kind of a very important questions. And let's see that. But let me just park that here. The short answer is that we don't know well. The exact position, of course, there is not an easy way that we can know about, but we can probably guess kind of few things. For example, this variable range hopping will give you the length scale. So this TES, Shklovsky, the temperature scale that allows us kind of calculate what is the length scale of the hopping. So it seems like the length of the scale of the hopping of that case is something like kind of close to 100 nanometers, something like this ranges. So we are not dealing with too many the things because the interferometer is about slightly less than micron in the diameter, so it's not much. The other hint is this anyon must comes from the edges because any charges that I have in the interferometer reside charge is electron to create only 3 anyons. Right, I cannot just change anyon numbers in that way by mode 3. So seeing these things, it comes from only the anyon reservoir we have is edges, which is kind of continuous reservoirs. So it comes from the edges somehow. That's kind of number 2. The other thing is that when you see that this interference by changing the magnetic field and all these things, you see that this phase is really, really stable, right? So which means over the many of the anyon got kind of changes potentially, or at least the 3 anyon state got changes. So we know that this cannot be too close to QPC because what happens is if it is too close to QPC, when anyon is happen to be occupied there and changing the electrostatics there, then our QPC got kind of modulated, and that would certainly kind of modulate this interference a lot, especially its visibilities. So not seeing this one that we know that anyon cannot be too close to QPC. So that's kind of the speculation we have. Where it is a little bit kind of difficult, kind of we can just say out of this one. The paper that I showed, the Andre Young group's paper, I think they did a little bit more careful work in a sense that there are more gates around, right? So tuning this gate and that, we are only changing the one plunger gate, but in principle, you just change this gate and that gate, many different combination. You can tease out a little bit where the potentially this anyon traps kind of located. And it seems like they have some idea that how many is a little bit difficult, but yeah, where the certain anyon traps are located in that way.
Maybe, is there any term called anyon compressibility in these systems?
In principle, you can do that. I think I don't have any quantitative way that you can measure it because once you have the puddles there, which means that it was kind of anyon number got in principle got changes, right? But how this kind of changes, that itself, I'm not sure the even theoretical answers there. I mean, probably theoretical answer might be there because anyon is not a fermions, right? So is it? Do I start to think about the? I mean, of course, Pauli exclusion principle may not work it out anymore, right? You can define the compressibility per se, but how that behave, I think this is kind of interesting questions. But I don't think that I don't have the answers, but I think this is kind of interesting thing to explore indeed. Yeah.
All right. Any more questions? Okay.
Any questions online?
Oh, okay. Yeah, online. Oh, there are people.
No,
online,
no, no,
sorry.
there doesn't seem any.
Okay. Yeah. Andres. Yeah.
Quick one. On the second work of the topological insulators case,
Yeah.
you were mentioning this 4 pi shift of the diode effect.
Yeah.
For this diode effect, of course, you need the inverse symmetry breaking and time reversal from the field, but you also need a current phase relation that is anomalous, right? That is not sinusoidal.
Yes. Yeah. 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 Good.
Where would this
Yeah.
be coming from?
Yeah, so that's that you already probably see that our transparency of the Josephson junction is 0.7 or about 0.7, right? So it is a kind of rather transparent. So you can see that the skewness of the IV, the current voltage characteristic is expected with such a high transmission junctions. Although we didn't measure, we could measure at this point that what is current phase relation per se, precisely. But just looking at this transparency that we estimate, I think it's a kind of natural to assume that, yeah, indeed, kind of high harmonics should comes from
Yes, yes.
this high transparency.
Thanks. All right.
Okay. All right. So then with this, let's thank Philip again. Thanks a lot for all the 3 days.
Thank you
For coming. And